Right. Welcome to our meeting, and let's start with some physics news for today. First, there's the announcement for our new series of SAT2 physics videos. And Rohan is going through the process of uploading them. And we also have a Discord, and our club meetings can also, recordings can also be found on VClubs.
So here is this week's physics news. It's regarding gravitational wave astronomy and some successful tests of Einstein's theory of relativity. So here on this visual at the right, you can see that we have a lot of black holes and neutron stars, which were detected by LIGO, Laser Interferometer Gravitational Wave Observer, and it's the LIGO Scientific Collaboration and Virgo Collaboration. So it's like an international team of scientists. And so there were three key papers that they made. They made a catalog paper for detection of black holes and neutron stars. They made populations paper for the mass and spin distribution of black holes and the merger rate for binary stars. By the way, binary stars are stars that will orbit around a common center of mass. And then we have another paper for testing the general relativity, which is some detections. And that's putting constraints on the general relativity, just from the catalog paper above. And so the source of all this is from this link right here, which was produced by Northwestern University, this article. So you can see this visual on the right. I know it's a bit hard to see, but the blue is all the black holes. There's a lot of those. Towards the bottom, there's an orange. And, between those, there's like three gray dots. I don't know if you can see those, but that's the uncertainty. The orange ones are the neutron stars and the blue ones are the black holes.
So this is our photo for today. Since we're talking about light, we will introduce the penumbra. This is a phenomenon like related to shadows of objects. So when we are talking about real objects, they are not just one point source of light. They're like a collection of light source. And so we see the sun, we can understand this phenomenon. So sun is a sphere, and you can see there's a very dark shadow behind the Earth, and that's an area where no points on the sun can directly reach because light travels in a straight path, and that's umbra. So penumbra um, is a partially dark area where it can be reached by some of the light source, but not all. So for example, in the lower end, you can the light source, like from the lowest point, it can reach that lower penumbra area, and but not like the uppermost point. And on the left is a real life example of this. So you can see P and E, because they are very close to the light source. They have a pretty big penumbra area because when it's close, the upper line and the lower line, they are not very parallel. So they will cause like a very big difference in angle. So when it casts shadows, there will be like a blur area. Well, like R and A, they're very clear because the lines are already very parallel, and so the shadow is crisp. But today we will learn, so like in a space sense, there will be curvature of light, and we will explore. So that introduces us to our topic for today, which is general relativity.
Okay, let's get started. So today we're going to be introducing the general relativity. So in the past two sessions, we talked about special relativity. It was about like the motion of an object and how the time and distance is like changed and how they are transformed by the Veron's factor. Today we're going to be talking about the general relativity. So so Einstein, he developed the general relativity between 1907 and 1915, and because of this theory, he has overthrown many assumptions about the gravity, and he like proves gravitational force is actually not a force, and it's actually a manifestation of the curvature of the space-time background. So let's, can you jump to the next slide? So let's talk about its history briefly. So the beginning of general relativity germinated in 1907. He first thought, what does like a free falling object feel like? It's actually like for an observer falling freely from the roof of a house, the gravitational field does not exist. So like imagine if you're jumping off from a roof of your house, what do you feel? You can feel like the gravitational force, right? It's actually really interesting. Can you go to the next slide? So so in 1911, he published a paper predicting the gravitational lensing, which we will talk about in a few minutes. And he then formulated a theory of space-time that was purely geometrical, because at this time he couldn't really find a mathematical model to express his idea, because at that time the theory of differential geometry was not well developed. So, but after a few years of extensive research, by 1915, he had developed what are known as the Einstein's field equation. Okay. So we know in special relativity, all the physical phenomena are in the absence of gravity, right? For example, if on a space-time diagram, if you want to make a straight line curve, you have to exert a force upon it, right? But in general relativity, there isn't like a force on it. It's actually the curvature of the space-time is an intrinsic nature of the space-time. So in general relativity, the space-time is not flat like that in special relativity. Yeah. Can you?
So you can imagine so all objects moving in free motion will move in a straight line across the space-time. But when there is something that has mass, the line are curved so that the object will move in a round motion, and this curving is gravity. So the object is not affected by the force; it's only affected by the change in space-time.
Yeah. So if you look at the world line in space-time diagram, if you want to make it curve, you have to. It's actually the effect of the gravitation of the space-time background. So let's talk about the equivalence principle in general relativity. So Einstein said there is no experiment that can be done in a small confined space that can detect the difference between a uniform gravitational field and the equivalent uniform acceleration. So imagine if you're in an elevator, it's a small confined space, and you can tell the difference. You can tell like whether you're on Earth or you're accelerating in space, right? All the physics laws are the same in these two confined space, in these two elevators. You can tell. You can like try to like drop an object, but you can actually they're all the same. Yeah, you can't tell the difference. Okay, let's move to the next slide. So let's talk about the result from the equivalence principle. So in a small confined space, if a photon is emitted from the look at the the picture on the right, is emitted from one side, if this like space is accelerating, it's stationary, the lines of the photon, it's gonna be straight, right? It's right to the like that, right? Um, if this small like confined space is accelerating, it's all bent down, right? Because it's like there are like numerous photons going that way. If you accelerate the speed, the path of the photon will be like a curve, right? So based on this, the equivalence principle we just talked about, we can assume like the light, the path of the light is curved near massive objects, right? Yeah. So let's move to next slide. So this gravitational effect was first, no, actually, let's look at the picture on the right. If there is a massive object, like whether it's a black hole or a star or something, if you observe a star that's really far away, if you you see it's this straight line on the right, this is the position of star we see as an observer here. But in fact, this is not actually not the case, because when the light travels near the massive object, it all bent. So the star is actually on the like little left of the the position we observe. So this is also known as gravitational lensing. So there were two classic tests of general relativity. The first one was that it should be deflected by passing close to a massive body. This is what what we just talked about. And so in 1919, they observed such effect during a total eclipse. And the second one was detected recently when observer the Mercury. Yeah, actually a few years, a couple of decades, like 2 decades ago, probably. And yeah, so the measurements of the cellular precision near the darkened solar lamp proved Einstein was right. Yeah, and this is actually a direct confirmation of gravitational lensing. Yeah, and okay, and yeah, and Hubble Space Telescope found actually found like took a no like was gravitational lensing was obtained by the Hubble Space Telescope last year. I'll show some images in the in film. Yeah, this is actually two pictures. Hubble's no, like the picture on the right was taken by Hubble Space Telescope, and as you can see, all the lights are all the like the bented, like because of the massive objects there. It's probably like a massive galaxy or a black hole that has bented the light that travels to us. And here's a video, and you can, Rohan, can you click on the link here? It's really short. It's like 10 seconds. Ish. Okay.
I sure downloaded it.
Oh, okay.
See if this plays.
Yeah, it's very short. Yeah.
Okay, it can't play.
Wait. Okay, never mind. It's just a short video about how the light is bented. It's thinking it so never mind. Can you go back to? Okay, so let's talk a little bit non-Euclidean geometry. We know like in high school we learn geometry, right? We learn how to prove how the lines are parallel or the triangle, stuff like that. This is Euclidean geometry, right? We are dealing with these objects in a flat space. But in Riemannian geometry or non-Euclidean geometry, uh, all the axiom do not hold true. So technically, Riemannian geometry is a branch of differential geometry that studies smooth manifolds with Riemannian metric. This definition is really technical, but I'll explain them one by one. So, you know, so what is differential geometry? So differential geometry is a field of math that use calculus to deal with this object. For example, can you go to the next slide? If you have taken some like calculus, this is an example of the basic differential geometry. For example, if you like take the derivative of a vector value function, you'll get the tangent vector, and the second derivative is probably like the normal vector or something, and the curvature as well. And the yeah. So I look at the picture on the right. This is a 3D classic differential geometry that has been developed like 200 years ago, probably. Yeah, and there are some basic differential geometries. They're using like calculus to deal with these curved lines. Yeah. And can you move to the next slide? Yeah, these are, I don't know if you guys can see it clearly. These are like two pictures of what modern different geometry is like. You can really visualize these objects. You have the only thing you can do is to derive like this like formulas from the step by step. It's really complicated, and yeah, and this is like under a graduate level course in math major. Yeah. Okay. Can you? So let's talk about smooth manifold. So manifold is in mathematics is a generalization and abstraction of the notion of a curved surface. So what does that mean? So we know like we have like in math we know lines and like a curve or a surface or a space or a 3D space. So they are all some sort of manifold. So like what do I mean by that? They're all like let me actually explain it in some mathematical terms. So a manifold is a topological space that is modeled closely to Euclidean space locally, but may vary widely in global properties. So imagine, so look at a tiny patch on Earth. You will see that all the lines are flat, right? If you can tell that like that the Earth is a surface while you are standing here, right? But if you observe Earth, if you can tell like the Earth is a sphere, but and because all the lines are flat, they are all some resemble the Euclidean space. So Euclidean space is a space that we usually deal with in like whether geometry or pre-calc or calculus. It's a flat space. Like a 1D Euclidean geometry is just a line, and 2D is a plane. 3D is like a 3D, right? But so because it's locally like a Euclidean space, this is called a manifold, right? So like the surface of the Earth is actually a 2D manifold, even though it's curved, but locally it looks like a Euclidean space. So yeah, this is something really interesting in manifold. Let's so what is most manifold? So imagine look at the picture on the right. There are three things, like two flat planes and one curved manifold or whatever. So they're like a map between the objects on manifold and the Euclidean. Actually, technically, it's a subset of Euclidean space. So if this map is infinitely differentiable, this is called small manifold. So like an infinitely differentiable function is like probably, for example, x squared. You can take it like first the derivative is 2x, and the second derivative is 2, and it then becomes 0. It's all differentiable. It's all well defined. This is called infinitely differentiable, right? So small manifold have like numerous nice properties. So they have been well studied in mathematics. So Riemannian geometry deals with some objects like this. Yeah. Can you move to the next slide? So let's talk about Riemannian metric. So we know like we have rulers, protractors to measure like a distance or length or angles, right? But on a manifold, like as we just talked about, like a curved manifold, you have to use something called the metric tensor. Actually, we talked about this in the past 2 sessions. Yeah, the metric tensor to measure like how curved the manifold is. So there are 2 examples of metric tensors in here. The first one on the left is the metric tensor in Minkowski spacetime, or the flat spacetime. This is the metric tensor used in special relativity, and this the second one is a metric tensor for a sphere, like a sphere. If you this is how like this metric tensor describes how a sphere is curved. If the metric tensor is determined, then the manifold is determined. Yeah. Can you move on? Yeah. So so Einstein's work, one Einstein's famous work is Einstein's field equations. So look at that. Actually, I use equations, not equation. This is because Einstein's equation is actually 16 equations. So because we use tensors, we can write them in a really concise ways. So this equation like describe how space-time actually look at the quote on the left. Space-time tells matter how to move, and matter tells space-time how to curve. Yeah, so this is mainly what the Einstein's field equations are about. And this is the most important result in Einstein's theory of relativity ever. Yeah. And yeah, can you move on? And I'm not sure if I can pronounce this right. Schwarzschild. Yeah, Schwarzschild Metric. Yeah, this is the result, one solution to the equations, to the equation we just talked about, the Einstein's field equation. So, and theoretically, physicists have been studying the equation for many years, and by solving these complicated partial differential equations, they found one solution, which is showing here. And this solution, or this metric, describe how a black hole is like a structure, the space-time space-time structure of a black hole. And yeah, this is really interesting. And like 2 years ago, I think a picture of they took a picture of a black hole or something. You can see like a yellow, orange color thing. Yeah, they actually took a picture of the black hole, and it actually proved people's theory is correct. Can you go? And I think that's it for today. And thanks for listening. If you have any questions about the math or the physics behind this stuff, let me know. Yeah. Thank you.
Thank you, everyone. Our physics video is currently up on YouTube for physics and waves and optics, SAT waves and optics. So it's a big accomplishment for the club. Thank you to everyone.
Great job.